Welcome to EPG Pathsala Architecture lecture series for MArch students. In this module, we are going to see further on wind energy and small hydro. And the learning objectives are wind power, that wind energy equations, case studies, lift and drag forces, and performance analysis of a wind farm, and small hydropower, current scenario, scale and schematic of small hydropower, and small hydropower, the components and the working principle. And as we discussed, so the wind farms, and it does not waste the land, and underneath the wind farm, underneath the turbine, and we can do the cultivation, we can do the farming, and agriculture will never be affected because of the wind farm, because the blades are far above from the ground level, about 100 meters height or 80 meters height, and it will never affect the field, it will never affect the agriculture, and as usual the agriculture can be carried out in the wind farm. And this is about the calculation of wind power, the power in the wind, that is half rho A V cube, and A is the swept area, V is the wind speed, and rho is the air density. And we cannot do anything with the velocity and air density, but we can do some modification in the swept area, so that we can increase the power output. Swept area, that is A, that is pi r squared, area of the circle swept by the rotor. So, this is the swept area, and as long as it is maximum, so the power output also will be the maximum. And how does the turbine rotate? The pressure difference makes the turbine rotates, and the wind attack the point, and here there is the high pressure wind, and here about the low pressure wind, and because of the pressure difference the turbine rotates. And so there will be the lift force and drag force, and the lift force helps to rotate the blade. The drag force will try to pull it down, but then this drag should be always minimized and the lift has to be maximized. And this is about lift and drag forces. The lift force is perpendicular to the direction of motion. The lift is perpendicular to the direction of motion. We make to make this force big, so the lift force should be big, and the drag force is parallel to the direction of motion. This is a drag force is parallel to the direction of motion, and we want to make this force small. So, drag force should be small and lift force should be big one. The BETZ limit. The BETZ limit is a important terminology in wind energy system. Theoretically, only 16 out of 27 of the wind power is recoverable. This is called Gilbert's limit or BETZ coefficient. This is the theoretical limit, and the P max, which is equal to 0.593 of P total. Approximately 60% of power could be recovered from the wind, and out of 100% only 60%, exactly 59.3% could be recovered. That is the theoretical output, beyond which no wind turbine can give output. So, that is the BETZ coefficient, that is a BETZ limit, and which is about 59.3, and that is about theoretical limit. And practically, and even if you achieve 40%, it is great, and this is the BETZ limit, and 59.3 is the maximum output could be recovered from the wind resource. And variation of power output and the wind speed. Actual power output depends on actual wind speed, rated wind speed, cut-in speed, and cut-out speed. And in this graph, it is well represented, and this is the cut-in wind speed. It is about 4 meter per second, and this is a rated wind speed, which is about 14 meter per second, where you can get maximum power output. And 17, that is cut-off wind speed, after which and it will be stopped automatically, and the power cannot be generated beyond this limit, because it will affect the system. That is why it has to be operated between 4 and 17 meter per second. Lower than 4 meter per second, it cannot be started. Beyond 17 meter per second, it cannot be operated. So, and it should be well between 4 meter per second and 17 meter per second, but 14 meter per second, and we will have the maximum output, that is the rated power output. Actual power output versus wind speed curve of a wind turbine is having rated power and wind speed of about 100 kilowatt and 14 meter per second respectively, and cut-in speed of 3 or 4 meter per second, and cut-off wind speed about 17 meter per second. And this is about the energy production terms, and here we have the power in the wind, that is half rho AV cube. As we have seen, rho is the air density and V is the velocity of the wind, and A is the swept area, and from the kinetic energy it is derived. The BETZ limit, it is maximum 59%, and power coefficient, that is C suffix P, and rated power, that is a maximum power generator can produce, capacity factor, actual energy divided by maximum energy available. Cut-in speed, cut-in wind speed where energy production begins. Cut-out wind speed where energy production ends. These are all very important terminology, and the BETZ limit is 59%, and the power in the wind about half rho AV cube, and rated power where you can get the maximum power, capacity factor, the ratio between actual energy generated and maximum energy generated, and cut-in speed where which is the speed necessary to start the machine, cut-out speed beyond which production ends. Production will be stopped automatically, otherwise it creates some dangerous problems in the machine. And here it is given the region 1 and 2 and 3, and the cut-in speed, and this is the rated speed, maximum power could be captured, and this is the cut-out speed, and beyond which the wind turbine will not be operated, and this is the power in the wind, typical power curve. And this is about extraction of wind energy, that is about the BETZ limit, how we arrive this BETZ limit, and how much energy is being extracted from the wind energy source. So, that is the derivation is given here, and this is the profile, pressure or velocity profile is given to understand the BETZ limit. BETZ limit, it is about 59.3%, which could be extracted, that is the maximum limit out of wind source. The energy from wind stream is extracted by a wind turbine by converting the kinetic energy of the wind to rotational motion required to operate an electric generator. Here the wind energy, the kinetic energy is converted to mechanical energy and then to electrical energy. And this is the profile about the BETZ limit, and here this is a blade, wind is flowing before the blade and the wind is coming after the blade. And so we make a two sector here, and before the blade and after the blade. And before the blade the wind is flowing and it is striking the blade, and then from the blade the wind is flowing out. And this sector we have I-A, and this sector it is B-E. So, we can call this is upstream and this is downstream. Upstream portion I-A and downstream portion B-E. And the small I, it represents the inlet wind velocity, and E represents its exit wind velocity, and the A, it is just before the turbine and B just after the turbine. And this is the two segments, upstream and downstream. And here we look at the pressure profile, and this is P suffix A, atmospheric pressure in the air, P suffix I, that is inlet pressure. And so, inlet pressure, that pressure of the air, it increases towards the wind turbine, that is the blades. So, the pressure of the, when the air is flowing towards the blade, the pressure kept on increasing, and that is in the upstream. In the downstream, the pressure and it kept on reducing, and here we see that it becomes atmospheric pressure, P, that is equal to P suffix E. So, here P I, it is in atmospheric pressure, P suffix E, it is also in atmospheric pressure, and before the blade it kept on, the pressure is increasing, and from this level, and in the downstream the pressure kept on decreasing. This is about the pressure profile. And when we look at the velocity profile, so the velocity, that is the Vi, that is the inlet velocity. So, it is maximum, and then towards the blade it decreases, and even after the blade it kept on decreasing, and then it reaches V suffix E. And uniformly the velocity towards blade it decreases, and even after the blade it decreases. And so, this is about the velocity profile. And how do we get, what is the BETZ limit? So, that for which the derivation is given, and these are some of the assumptions. The flow of wind is incompressible. So, we assume that the wind is incompressible, and hence the air stream diverges and it passes through the turbines. The mass flow rate of wind is constant throughout at far upstream and the rotor and at far downstream. So, the mass flow rate of wind before the rotor, after the rotor, that is in upstream level, at the rotor, after the rotor, it is constant, and the flow of wind is incompressible. So, these are the assumptions made to do the derivation, and these are the notations from the pressure and velocity profile. P, that is atmospheric wind pressure, P suffix I and V suffix I, pressure and velocity of wind on upstream of wind turbine. P suffix E and V suffix E, that is pressure and velocity of the wind on downstream of the wind turbine. V suffix R, velocity of wind at blades or rotor. A, area of blades or rotor. M, mass flow rate of wind, and rho, it is the density of the air. And here, to arrive the BETZ limit, here we are applying the Bernoulli's equation. So, from Bernoulli's equation it is arrived the BETZ limit. So, applying the Bernoulli's equation to upstream, that is I hyphen A, and downstream B hyphen E. This is the upstream and this is the downstream segment, and both the sides we apply the Bernoulli's equation. Equation number 1, that is the pressure P I and so kinetic energy, and then pressure at the downstream side, and this is about the kinetic energy, and so that is equation number 1, and this is equation number 2. So, we apply the Bernoulli's equation and the upstream side and the downstream side, and we create the equation based on the Bernoulli's equation for the segment upstream and downstream segment, and we have written the equation number 1 and 2 based on the Bernoulli's equation. And then from equation 1 and 2 we obtain, that is P suffix A minus P suffix B, and here this pressure we obtain from the equation 1 and 2. So, from equation number 1 and 2 it is written based on the Bernoulli's equation, then always substitution, rearranging, and we finally arrive the BETZ limit. Here from the equation number 1 and 2, and we have taken the pressure at A and pressure at B, and this is the after shorting we can arrive this equation and of P into V I squared minus V E square. Then that is about the pressure difference, and the force on the rotor disc, that is F is calculated. What is the force on the rotor disc? That is force is nothing but it is P suffix A and P minus P suffix B into A, and so this is the force on the rotor disc and area into pressure, and that is equal to, it can be rewritten like this, that is and here P A minus P B, that is the equation we got, and we are substituting here, and then A and equation number 3. And for the same force, there is another equation, that the force is equal to the change in momentum of the wind from the Newton's second law, and according to the Newton's second law we have the force that is equal to V I minus V E, that is equal to rho A and V suffix R and into V I minus V E, that is equation number 4, and we arrived equation number 3, it is also force, and equation number 4 it is also 4 based on the Newton's second law. Now, we are equating equation number 3 and 4, and so and both are force, and then we are equating it, and we got it V suffix R, that is half of V I plus V E, that is equation number 5, and the power output, the power of wind turbine, that rate of doing work is given as P, that is equal to half into V I squared minus V E square, that is equal to half rho A V R into V I squared minus V E square, that is equation number 6. So, from this we are substituting the 5 in equation number 6, again we are rearranging it, and we are getting P equal to, and quarter the 1/4 of P into A and to V I plus V E into V I squared minus V E square, that becomes equation number 7 after substitution. And to get P max, that is a maximum turbine output power, we are differentiating the equation number 7 with respect to V suffix E and equating to 0, then we get this equation. And the above quadratic equation has two solutions, that is V E equal to minus V I, which is impossible, V E equal to 1/3 of V I, it is acceptable. And substituting this V E, that is equal to 1/3 of V I in equation number 7, we get P maximum which is 8 by 27 into PAVI cube, and that is equation number 8. Then again it is rewritten P max, that is equal to 16 out of 27 into half PAVI cube, that is equal to 0.593 into PAVI cube, that is 0.593 P total. And so that is the maximum power output, and that is P total is half rho A V cube, that is power coefficient Cp, that is P max by P total, and power output from the wind machine divided by power available in the wind, then we get 0.593. That is the BETZ limit, and that is the ideal or maximum theoretical efficiency. Eta max, also called power coefficient of a wind turbine, is the ratio of the maximum power obtained from the wind to the total power available in the wind. This is about extraction of wind energy, that is the theoretical limit, that is the BETZ limit, and we arrive from the Bernoulli's equation, and we are equating the upstream and downstream, and we substitute the equations, and then we are rearranging it, and we are finding out force on that, and then again we are equating with the Newton's second law, and then finally we arrive the BETZ limit, the theoretical limit from wind energy, which is about 59.3%. The factor 0.593 is known as the BETZ coefficient. It is the maximum fraction of the power in a wind stream that can be extracted. Thus, C suffix P cannot exceed 0.593 for a horizontal axis wind turbine. So, that is the limitation, and that is the maximum beyond which no one can expect for further extraction of wind energy. And these are the leading manufacturers of wind turbine. And Vestas, it is a Danish company, it is in Denmark, and so they have installed about 35,000 megawatt capacity around the world. And the Vestas is a pioneering company. It is situated in all over the world. In India, there is the hub, there is the R&D unit, and in India, and majority of the turbines are Vestas, and this is Enercon, it is a German based company, and they have installed about 19,000 megawatt all over the world. Gamesa, it has come to Chennai, India. It is Spanish company. It is about 16,000 megawatt they have installed already. And we have Vestas and Gamesa in Chennai, Tamil Nadu, India. Both companies are here. One is from Denmark, another one is from Spain. And this is about the General Electric, that is GE, it is from USA and Germany, and it is about 15,000 megawatt installed capacity. Siemens, again from Denmark, from Germany, they have installed about 8,800 megawatt around the world. Suzlon, indigenous from India, we have installed about 6,000 megawatt out of Suzlon. Nordex, it is a German based company, 5,400 megawatt they have installed, and Acciona, it is Spanish company, and 4,300 megawatt they have installed already. Repower, German based company, 3,000 megawatt they have installed. Goldwind, again Chinese company, they have installed 2,889 megawatt. And these are the leading manufacturers of wind turbine around the globe. This is about large commercial wind turbines, and so the Vestas and GE and Gamesa, Enercon, Suzlon, and all these companies, and this is the share in the world market, and the Vestas stands at the top, and followed by GE, Gamesa, Enercon, etc. And these are the various models given. So, this is the drive train, and there is a power rating machines, and 3 megawatt machine and 2.5 megawatt machine, quite high capacity machines from 2 megawatt, 3 megawatt. It has become very common. This is the diameter of the blade, the rotor, and this is the tip speed, and this is the power conversion. And so, these are the large commercial wind turbines, and the expected output, the capacity factor. So, the capacity factor is the power coefficient, or we can call it, it's a maximum, that is the efficiency factor or load factor. That capacity factor is simply the wind turbine's actual energy output for the year divided by the energy output if the machine is operated at its rated power output for the entire year. Suppose if the wind turbine is operated entire year at the rated speed, and so what would be the capacity factor? And the reasonable capacity factor would be 0.25 to 0.3. The capacity factor is from 0.25 to 0.3, it is good. A very good capacity factor would be 0.4, beyond which it is difficult. But we can go up to 59.3, that is 0.59. We have a long way to go, to achieve the BETZ limit, but practically there are some difficulties. Even if we achieve 0.4, that is 40%, it is quite good. Capacity factor is very sensitive to the average wind speed. The average wind speed, the annual average wind speed should be quite high, it should be quite good, so that capacity factor can be derived maximum. That is, capacity factor is very sensitive with the average wind speed. Then the land requirement, and generally the land required will be highest for wind power systems. When we take this is in say hectares is given, and this is for 1000 megawatt installation. For example, for 1000 megawatt of coal based technology, it requires just 250 hectares of land, whereas natural gas based power plants, which requires about 100 hectares for installation of 1000 megawatt capacity. Nuclear, and for 1000 megawatt reactor, it needs just 250 hectares of land, whereas solar, for 1000 megawatt installed capacity, it needs 2500 hectares of land, and these land cannot be used for any other purposes. Whereas the wind, of course, it needs more land area when compared with other technologies. It needs, for 1000 megawatt of installed capacity, it requires 3000 hectares of land, but then it is not wasteful. Underneath the wind farm, underneath the wind turbine, again we can, without wasting the land, we can do agriculture, we can do the cultivation, and without wasting the land. And so in this lecture, we have seen so far about the land requirement and the BETZ limit. Importantly, we have seen that how much energy could be tapped, and we have seen the derivation from Bernoulli's equation, what is happening in the upstream and what is happening at the downstream, what is happening at the rotor, and we are equating and we are arriving the BETZ limit, which is about say 59.3. And so the maximum capacity factor we can go up to that 59.3, but because of the practical reasons, we can, the best turbine could perform 40% with 40% capacity factor, and generally the wind farms capacity factor would be around say 0.25 to 0.3, that is 25% to 30%, but the best wind farm performs about 40%. Of course, there is a very good wind farm in Muppandal area, southern part of Tamil Nadu, where some of the wind farms could give up to 40% capacity factor, because the wind velocity is quite good. After California, that is the best site in the world, and after that, and India is having the best site, particularly the Muppandal area, southern part of Tamil Nadu, where you can get capacity factor of about 40% also. And people are doing further research in order to increase the capacity factor, and for which they have to select the right site, which the annual wind speed should be in the order of 10 meter per second, and it would be the best site. And if it I mean, most of the turbines, if it is operated at rated power speed, definitely the performance will be very interesting. And so the further research is needed to bring down the cut-in speed, that is currently it is about 4 meter per second. If it is brought down to 3.5 or 3.75, and definitely the potentials could be increased, and the installations can be increased. And other than that, the composite materials are being used in the components of the wind turbine system, and mainly the composite materials, and the material should give very good strength. At the same time, the weight should be reduced, and people are doing further research in the area of materials, wind turbine, wind energy system materials, as well as they try to do better design for the blade, so that even at the low speed it could be operated. And all over the world, there are lots of multinational companies in Europe, in US, and China and India. There are multinational companies, and through these companies an enormous amount of wind turbines are installed all over the world, and it is quite mature technology. And of course, with the further research, the efficiency could be further enhanced, the downtime could be minimized, and it needs better maintenance, so that and the downtime could be minimized, and effectively we can generate electricity. And with this, I stop this module. Thank you for listening.